good morning. And first of all, thank you to Sudipto for the opportunity to talk about this very interesting topic on which the Nobel has been awarded. Thanks to Dr. Kumbar and the library team for organizing these series of lectures. It's very nice. Yeah, all right. So I think most of you know me, but for those who don't, who are not in physics, my name is Prasanna. I'm a faculty here in the physics discipline. My research area is in theoretical quantum optics broadly and open quantum systems. All right. So today I'm going to talk about, as this slide, if it changes, shows. Okay. It's just a starting trouble. Come on. Is that thing on? This is on. Is there an on switch here? It is on. It is because I think it is via Zoom. It's taking probably a little bit longer. Just give me 1 second. Maybe just USB in, USB out. The only kind of experiment I know. Let's see. Let's see. No, this is bizarre. Let me try again. What? इसका बैटरी खत्म हो गया क्या? Last time हुआ था. Yeah. Oh, you have one? Ah, a real experimenter to rescue. It's always nice. He thought about it. Good job. If this doesn't work, you will. I can quit this. Okay, wait. Quit. Continue करना है क्या? हो गया? Okay. All right. You can give the talk as. All right. So, it's a pleasure to talk about this year's Nobel. So let's get along. Let me begin, because there are also people who are not in physics in the audience. Let me briefly begin by essentially talking about what this year's Nobel Prize is about, in some sense, in the most broad way. And hopefully, even if you don't get the rest of the details or the details within the rest of the slides, hopefully this will help you go away with a message. Okay. So, as always, the Nobel Committee is very good with the citation. So that's a good place to begin. So this year's Nobel was given to Alain Aspect, who's French, John Clauser from the US, Anton Zeilinger from Austria, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. This is a picture of John Bell, who's an Irish physicist, who is, in some sense, the invisible driving force behind all of these things, as I will try and tell you. So what exactly is this all about? So this whole thing goes back to a very bizarre property of quantum mechanics, which tells us that quantum systems do not have properties. There is no meaning to properties of quantum systems until you actually measure them. Okay, so this is an extremely bizarre situation when you compare it to your classical intuition, because classically, whether you measure the speed of your bicycle or not, whether you measure the speed of your car or not, there is a certain value that is there. All that measurements do in the classical world is they uncover pre-existing values of physical observables. But this view, which sometimes is called as realism, this does not apply to the quantum world. Okay, and this is part of the foundational postulates of quantum mechanics. And Einstein, as with many good ideas, this whole thing goes back again to Einstein. He was a very sort of staunch believer, or in some sense, he loved the intuitive nature of classical Newtonian physics, and he was not willing to give up this realism idea very easily. And then he went out to show that what I called as a feature or a property of quantum mechanics is actually not a feature, but probably it's a bug of quantum mechanics. So how he did this, he, along with two of his colleagues named Podolsky and Rosen, so the set of phenomena I'm going to initially describe are many times called EPR. What they did is they considered a quantum system which was prepared in very special correlated states, which nowadays we refer to as entangled states. And what you did is you initially prepared them in these entangled states, and then you basically divide this system into two subparts. and you remove them physically very far away, okay, as far away as you want. And then what you do is you do one of these measurements. As I said, in quantum mechanics, you can do a measurement. We'll come to the details. You do a measurement on one part of this system. Then what properties of quantum mechanics tell you is that you immediately know what are the results of a measurement on the other part is going to be. Okay, this is extremely bizarre because in principle, I could have separated them far, far away, many galaxies away. Doesn't matter. Even then, quantum mechanics tells me that if I do a measurement here, I will know what's going to happen there. So Einstein called this weird, spooky action at a distance. And this went against a cherished principle of physics, which is called locality, which basically tells you if I want to influence some point far away, I have to influence all these points in between. So my influence as a physical system cannot extend for infinite distances. Okay. And he said, okay, so this is bizarre. So I have to preserve locality, which means his idea was that this is a bug. So it cannot be that quantum systems actually, properties of quantum systems are not established only when you measure them, but you have not yet understood quantum mechanics well. He went with a theory which he said quantum mechanics is incomplete. So in order to understand how quantum mechanics would really work, we have to actually add objects called hidden variables to the quantum system's description itself. And these hidden variables will tell you exactly how the results of a measurement should work. It's not that this measurement on this subpart is influencing a subpart far away. It is just that you didn't know how the measurement was working. So what was somewhat interesting is that even though this is a very fundamental and weird feature of quantum mechanics, and Einstein sort of hit the nail on its head to show what was happening, for a long time, this phenomena, this EPR idea, was relegated to essentially what you would call as philosophy of physics or metaphysics. One of the reasons was basically what Einstein found was that the bug was not sort of a bug that killed the predictions of quantum mechanics. It was basically telling you that whatever description you're using to describe quantum mechanics is not complete, but the plethora of experiments that you could do purely believing in quantum mechanics as it stood at the time of Einstein, nothing was wrong with them. And this meant a philosophical position that was taken by another very famous quantum scientist, Niels Bohr, where he said, well, deal with the fact that quantum mechanics is not a realistic theory in the sense that you have properties only when you measure them. Just deal with it. And this stood basically, this was the situation for a very long time until the 1960s, when Bell basically came along and he took the idea of Einstein and ran with it. What he did is, okay, so you're saying that there have to be some hidden variables. Let me make some hidden variable model. And let me actually construct this EPR experiment with hidden variables. And then I calculate the properties of the system, what these hidden variable theories predict. Now, he showed that no hidden variable theory, which is constructed to be local, because we want to keep everything local, no hidden variable theory, when you construct it in this local fashion, can explain all the results of quantum mechanics contained within this EPR, contained within this original idea of Einstein. And this he expressed by the way of a certain set of inequalities that are followed by theories which are quantum mechanics plus this incompleteness plus these hidden variables. So these inequalities are what are called as Bell's inequalities, but he didn't stop there. He basically said, now let me tell you, if I make my quantum system and my experiment of EPR in a particular fashion, I can show that quantum states will violate those inequalities. So this means that I can actually design an experiment to disprove hidden variables theories, which meant that he brought what was actually just metaphysics into the realm of actual testable, experimentally testable physics. Okay, and that's the point where our Nobel Prize winners enter the scene. So very briefly, John Clauser was the brave man. I'm calling him brave for a very specific reason. He's an experimentalist who dabbled with metaphysics. So experimentalists who are in the audience can think about how crazy that is. And he succeeded at it. And he was the first one who basically took Bell's inequalities, converted them into an experimentally testable form, and did the experiment. The first set of experiments showing that really quantum mechanics is as bizarre as it sounds. Then the second person, Alain Aspect, he entered the scene a little bit later. He did some very important things, which is there are certain assumptions that are within the original experiments of Clauser, which could still not disprove some classes of hidden variables theories. So he actually helped plug these so-called loopholes, which would help basically reinforce Einstein's original idea, but he helped plug those loopholes. But in the process, he also managed to sort of make very, very important improvements to the way we did experiments with entangled objects. Okay, so he did a lot of work on pushing the experimental science. And finally, the third person here, Anton Zeilinger, he essentially perfected this art of making experiments verifying violations of Bell's inequalities. But not only that, he kind of realized that this idea of entangled or strongly correlated quantum states, it's not just a test bed for testing, Bell's inequalities, but entanglement is the resource, is the central resource that fuels all of quantum information science. And he made entanglement useful. And he did a bunch of very important experiments that basically used entanglement as a resource. Okay. So I realized that this was not really a nutshell, but still, I think this is the talk in some sense. So if you want in the broadest sense, here I can sort of even stop the talk and we can all go. But since there are lots of physicists also in the audience, let's go a little bit deeper and get through this. Okay. Any questions at this point? No? Too fast, too slow? Okay, anyway, I'm going to explore all of these ideas in as slow as possible. And please feel free to ask questions. So I have a slightly large talk outline, but don't be discouraged by it. My aim, in some sense, is to start a conversation. So even if I don't get through it, I'll be happy. So the first 3 parts of the talk is all about the bizarreness of quantum mechanics, the basic idea behind these Bell's inequalities with as little math as possible. And then I'll get to the experiments, and I've devoted a section each to the 3 laureates. And then we'll conclude. Okay, that's the broad idea, but let's see how far we get. Huh.
Does it mean that the idea of determinism is totally
What do you mean?
determinism in terms of classical physics? It's totally knocked out of physics.
That was knocked out when quantum mechanics postulates were established. At that time itself, it was clear that it's not deterministic. Realism is a little bit different. That's what I was trying to say. Because determinism, you can also lose from, classical chaotic systems or at least like probabilistic systems of any kind, like statistical mechanical systems also don't have determinism in the strict sense. So, but yeah, anyway, so we'll see. Huh. What is real? What is element of reality? This is a very interesting question. This is actually where it is a bit metaphysical. So what I mean is like, in principle, in the most, let's say, pithy way of saying, am I here when you're not looking? If I were a quantum system, the answer is you have to first do an experiment. Otherwise, you can't be sure. That is what I meant. In the classical world, this is not an issue. It's very clear that what we think of as usually real is indeed real. So there's no issues with that. But in the quantum world, this is not the case. Okay. All right. So let me begin with a very slow and basic introduction to quantum mechanics so that we have a common language so that we can understand the full import of all these ideas. So I'm going to begin by talking about how quantum systems can be described. How do I describe a quantum system? For instance, I'm going to always be focusing on systems which have just 2 configurations or 2 states. These are the simplest kind of systems in quantum mechanics. So before I go to the quantum case, let me think about the best or the simplest 2-state system you can think of in classical physics. This is the idea of a classical bit. Here, I'm showing one possible physical way of thinking about a bit. It's like a magnet which can point up or point down, north-south or south-north. That's one way. A second example of a classical bit. This is always going to be a problem because I think, come on. Didn't want to do this with Zoom because of this. Yeah. Huh. Yeah, there is a finite delay. Or maybe I should point to this. Maybe it is due to this. Okay. Yeah. Anyway, or you can think of another very simple bit-like system in classical physics, which you use every day, which is a coin, right? I have a head, I have a tail. So these are like, and I can describe these states by integers, 0 or 1. My classical bit system can either be on or off, head or tail, north-south or south-north. So this is the description of a classical two-state system. So now let's come to quantum two-state systems. I'm going to be using these terms interchangeably: qubit, spins, eventually something called polarization of photons. But all of these terms are going to refer to two-state systems in quantum mechanics. It turns out that the best kind of two-state system I can think of in quantum mechanics is physically an electron and its intrinsic degree of freedom called spin. Okay, and that's what I'm depicting here in this picture. This is the spin of the electron pointing up, spin of the electron pointing down. You don't have to think too deeply about spin for this talk, but all that it is, you can think of these electrons as tiny versions of these magnets, and these as the magnetic moments that point up or point down. Okay, that's all. And here I'm introducing a second notation for quantum mechanics, where the state of a spin of the electron when it is pointing up, I'm going to always use this kind of depiction where there is one line and an angled bracket, and the information regarding the state, whether it's pointing up or down, is put in between these brackets. So these are called state kets within quantum mechanics, but just remember, because these symbols are going to float around, it's very hard to do this talk without any symbols. And then these are called upspin, and this is the downspin. At this level, basically, there's nothing very different between classical and quantum mechanics. Yeah, the spin can point up, point down. This is pointing up in some direction in space, pointing down in some direction in space. It's just like a thumb up and thumb down. Nothing interesting is happening at this moment. But then what can happen is, apart from these states, quantum mechanical qubits or qubits can also exist in a very strange state, which is called superposition, which is a linear combination of the spin being up and the spin being down with some mutual, let's say, relative weights. So these relative weights are given by these numbers C up and C down. And these are in principle some complex numbers. But the idea is that visually, whenever you do this, you can think of the spin as being canted to some direction in space. It's not up, neither down. It's canted in some direction in space. Okay. And these are superposition states. So that's the main thing you want. That's the first feature of quantum mechanics one should understand, that unlike a classical bit, I can have these weird situations where I can put a quantum mechanical system into the state which is sort of pointing both up and down. Okay, I'm going to come to the next bizarre kind of thing that quantum mechanics tells us. But before that, just for the people who are mathematically inclined in the audience, I can actually mathematically represent this upspin as a simple column vector 1, 0, and the downspin as 0, 1. Then this allows me to represent this weirder object as basically another column vector that you might have seen in matrices and matrix mechanics, C up and C down. So this actually should tell you that the natural mathematical language of quantum mechanics is vectors and linear algebra. Okay, just a small side note. Okay, so that was one aspect. But now let's come to the second and the most bizarre aspect of quantum mechanics, which is what this whole EPR and these Bell's inequalities are about. This is the idea of a quantum measurement. So instead of the spin pointing up along the Z direction, if I could make the spin, I can do this in a lab, I can make it point along the X direction in space. So this is, the Z direction is up, X direction is along this. Now, the quantum state of such a spin, I can write it as an equal linear superposition of the up and down. Don't ask me how I can do it, I can do it. All right, because that'll get far away. And now I can ask this question. Now let me actually do a measurement of the spin of this electron or this qubit. And now I ask, interestingly, if I ask when the quantum system is in this state, is it pointing up along Z or is it pointing down along Z? Remember, it's a linear combination of these two. Quantum mechanics gives you just the following answer. It says, throws up its hand and says, I cannot give you a definitive answer. I can only give you a probabilistic answer. It tells me that there is a probability of half to find the spin up, and there's a probability of half to find the spin down. And this can be generalized further if you want the spin to point in a different direction and so on. Not so important right now, but let's move on. Okay, good. And now I want to actually, I've given you this probabilistic description of quantum mechanics, but to make it a little bit more tangible, let us actually understand and visualize how would this probabilistic description play out if I did a toy experiment based on quantum mechanics. For this toy experiment, what I'm going to do is I'm going to make many copies of my system. Okay, and each element of this copies, sometimes these are called ensembles, these are prepared in exactly the same quantum state, which is this state pointing along the x direction. Then I'm going to do a quantum measurement, which I'm literally depicting it as a black box. Okay, what this black box will do is it will take each of these states and it will spit out an answer to you. It will tell you if the spin is pointing up or down. So imagine this is an infinite sort of array of spins, one after the other, that enter this black box and will come out the other direction. And let's see what would happen in such a case. Okay, what would happen is as follows. First spin comes through, the black box spits out the answer, spin is pointing up. And then please notice carefully, when the spin comes out, it actually comes out in the state that it was measured, which is extremely important. It went pointing in the x direction, it comes out pointing in the z direction. That is also a very important aspect of how measurements work in quantum mechanics. They change the state of my system. Okay, let's play this a bit more. So I do another particle goes in, it also spits out up, and then I do another one, suddenly I see a down, another one up, down, and it keeps going on and on and on. And what this probabilistic description tells me is individually, I can never tell, individually as particle stream out, I can never tell you, is it pointing up or down? All that I can say is if I have 1 million of these, half of them roughly will point up, half of them will point down when I do a result of a measurement. That is the idea of when I said measurements do this. And this completely is a big departure from realism, as I said, because even though if you imagine that the spin being up or down is just something that is already there within the quantum state, that is not the case. So it's not, the spin is not, before you measure, the spin is not pointing up or down. You do not know what it is doing until you measure, which is a big departure from, let's say, how you would think of classical systems. If I have a classical coin, it's either head or tail. I just have to spin it and then look at it, right? It's not like my act of looking has created the head or tail, but that's not the case in quantum mechanics. And that is this departure from classical realism that Einstein was so worried about. Any questions so far? Yeah. So, but that is the idea of realism, right? There is no true nature. So only realistic theories have this idea of a true nature. So you ask, what is realism? That's a very good way of saying what is realism. There's no such thing as true property that exists before measuring. In quantum mechanics, it all comes from the measurement. That's the idea. Any other questions? It's far away from my talk. I'll get to it later. Yeah. Any other questions?
So how to design the test on that? It depends on how it lands up, right?
Yeah, I mean, what is very interesting is this is not, and that's a very good point. This is not something I can sort of do away by making a better and better measurement. It's not that I'm not looking hard enough. This is an in-principle issue with quantum measurements. It's not that if I make a better measurement apparatus, I will be able to predict whether it will go up or down. It's not a measurement apparatus error. It's just the way quantum mechanics is.
My question is, for example, I designed the experiment in a different manner so that instead of,
Yes, I can.
It becomes a little bit. So basically, I'm
wonderful.
Wonderful.
Wonderful. So that is completely possible. For example, let's do the two extreme limits and something in between. So for instance, instead of asking whether the spin is pointing up along Z, I can ask whether the spin is pointing along X. In that case, each time I know what the answer is going to be. So I have to also have a particular kind of state where I do not know the answer. Secondly, if I put this detector to ask the question, is the spin pointing along the 45-degree axis in the XZ plane, right? I can ask that question also. Then I'll get a different answer in terms of what is the fraction of spins that will point along this way or this way. Okay. That was the dot product I was writing, which I didn't go into details. Good.
When you're saying if I was asking along X, then I would get exactly the same answer every time.
Yes. There's no problem with X. Yeah. It's important. The state is also important. What you get out. And that is important in any sort of measurement, right? The state also influences the results of a measurement. Okay, good. All right. So now, to explain this slightly bizarre nature of this lack of realism or lack of true nature of my system, let me push before we get to this Bell's inequality stuff, which is a little bit more involved. Let me actually talk about a very bizarre situation that you can get even without going to Bell's inequalities that arises from this lack of property before measuring it. In this case, I'm doing exactly what I was doing before. I send a stream of qubits that are all pointing along Z direction. I put it along this. I ask a quantum measurement, is it pointing up or down along the Z direction? It's coming along X. Then, because I know this idea that the spin, if it points along X, it's an equal superposition of up and down. If it points along minus X, it is an equal superposition of, again, equal superposition of up and down, but with a factor of -1 in between. Okay. Because I know this, I know what's going to happen because this up spin along X is equal superposition of up and down. As I just described in a slightly more cartoonish way earlier, half of my spins will go up, half of my spins will have spin down. Now, let's say I have some experimental mechanism where I can filter these out. So I can make magnets that are pointing up move this way, magnets that are pointing down this way. This is easy to do. I just apply a magnetic field, right? So that will apply a force that is different, and one stream will go up, one stream will go down. This can be done. I do that, and I first do the following. I get rid of all the down spins. I don't play with them at all. I basically just destroy them, whatever you want. And then I take all the spins that are pointing in the direction up along Z, okay? Now, I can basically invert this relation now to understand what is the answer going to be if I send a bunch of spins pointing up in the Z direction and ask the question now. When I have this black box and X written, it means I'm asking the question, is the spin pointing along plus X direction or minus X direction? Precisely the same thing happens. I can rewrite this expression and say basically, if my spin is pointing up along the Z direction, it is an equal superposition of up along the X direction, down along the X direction, or forward along the X direction and backward along this X direction. Which means as soon as I send these up spins in the Z direction through this X, again, I'll get two equal streams. And in these streams, I'll have spins either pointing, equal number of spins pointing along the X direction, forward or backward, okay? And this will also be an equal stream. And now, lo and behold, I get rid of the spins that are pointing this way, I destroy them, and then I make these guys pass through a Z direction measurement again. What happens? Amazingly enough, I get both up spins in the Z direction and down spins in the Z direction. Let me tell you why this is bizarre. Because see, at this point, all of these spins were pointing up in the Z direction. And suddenly, purely by measurement, I've manufactured for you half the spins down and half the spins up. So that is the idea that is the main idea. This is a big blow to the idea that there is some true nature. There is no realism. It's all measurement that creates these results of measurements and measurement that creates the properties you observe in quantum mechanics. Okay. And this is not just a cartoon. There are like very famous experiments in physics that have done this to death. Okay. Good. Now, with that sets up the basic ideas of quantum mechanics. And now we can move towards the paradox that Einstein, Podolsky, and Rosen introduced. Questions? Yeah. Correct. Sequentials turn together. That's all it is. Yeah. Yeah.
And your pulling the field along X and Y still in this statement kind of thing.
Yeah. There is some inhomogeneous field I have to apply. Okay, good. So now let's move to this is a bit of a subtle topic. So when I'm talking about measurements, I'm just talking about quantum measurements only in this talk. So what I mean is a measurement in quantum mechanics is a measurement done on quantum systems. That's all, nothing fancy. It uses the same sort of things. You will still need a ammeter, you'll still need a voltmeter, but you have to make sure that these can talk to quantum systems also. Yes, they are built. So and that's a very good question. That's a question about where the quantum world stops and where the classical world begins. That's what this guy was also asking. We will get to it in the end, if there is time. But that's a more deeper question. At the moment, everything is quantum. I'm not even talking about. These are ideal measurements which I somehow perform according to the postulates of quantum mechanics. Okay, so now we are in a position to talk about, in a more meaningful way, the most bizarre consequence of the lack of realism in quantum mechanics, as pointed out by Einstein. In order to do that, we need this very strange ideal source. What this source does is it prepares not qubits, single qubits anymore, but now it prepares 2 qubits in this very special state. I'll explain what this state is. It is a state of 2 qubits. There are, instead of 1 qubit, which I was talking about so far, now there are 2 qubits. This state is sometimes called as an entangled state, and this is particularly called as one of these Bell states after John Bell. What this is telling you is that the green spin, this particular, let's focus on the first part of this superposition, right? As I told you, it tells you that my green spin is pointing up and my blue spin is pointing down. Okay, so that's it. So it's a 2 qubit state or 2 spin state. One is pointing up, the other is pointing down. And then that is in equal superposition, equal because these factors are the same, up to plus minus, with another state where the green spin is pointing down and the blue spin is pointing up. Okay, that is the state in which my source prepares my spins. And my source can prepare many of this, because already you should hopefully have gotten one aspect of quantum mechanics clear, which is, if I have a probabilistic theory, one run of a measurement is absolutely meaningless. It's like tossing a coin. You will not know if your coin is biased or not by tossing it once. Right? Everyone on the same page? Okay. So this can produce many such pairs. Let's see what we do to each of these pairs. After producing these pairs,
plus and minus, right? And
you can. What? No, this is a very interesting state. So what it is now you're asking, let me rephrase your question a little bit. You're asking, which direction is it pointing up and which direction is it pointing down? Right? That's what you mean when you say this. Doesn't matter. This particular state, you can imagine that the spins are pointing up in X, pointing down in minus X, or Z minus Z, Y minus Y, arbitrary direction in 3-dimensional space up and down. That is a very special property of these states. So the basis is not important. But for explaining measurements, I will still use a basis. For now, you can imagine it's pointing up along Z, pointing down along Z. Yeah. Okay. And then what do we do? Now, after the sources produce these 2 green and blue spins in this state, I can now take each of these spins. Remember, spin is an internal degree of freedom. This spin can also move. This electron can fly apart. So imagine I apply some electric field or whatever and make these electrons fly apart to the opposite ends of space. No, this is a state which is in, how do I say it? What is the best way? So if this is a state which is sort of, they are independent in some sense. One spin is pointing up and the other spin is pointing down. So if you put this state alone, let's use the measurement I did along Z, then you will get one spin that will go up, one spin that will point down in the Z direction. Okay, so it's that kind of a state. So I'm trying very carefully not to use math. It's hard. Okay. All right. So any other questions? All right. So if not, now I can make these spins fly apart. And the fact that they were prepared in this very interesting initial state, which is called an entangled state, I'm denoting that by this dashed line that joins them. It tells me that they're not independent in some sense, right? And now let's imagine that we keep making them fly to the ends of the universe. Doesn't matter how far apart you do it. And then I do something. I can't hear you. Sorry. Subspace. No. These are but these are literally free electrons. It won't matter so much until I come to a real experiment where I'll show you when you can make such states with photons. For now, you can think of them as literally free electrons who spin. So I showed you these experiments where I made up spin and down spins with a measurement along Z, right? Imagine that somehow I bring two of them together. That's what this up down is. That's it. There is no linear combination involved within writing this. That's what I was trying to explain to him. So this is a system that has two parts, right? It has a green part, it has a blue part. It's not a single spin. Okay. All right. Good. And now I do a measurement now. What I do is I pull them apart far away and I do a measurement purely on the green part. And I ask the question, is the green spin pointing up or down? Okay, that's the question I ask. And imagine I get the answer in one of these experimental runs. The green spin is pointing up. Then let's look at this state, the way it is written. What is this state telling me? This is telling me that if the green spin points up, the blue spin has to point down, right? That's how I made this state, which means even without doing a measurement on the blue spin, I can tell you that if you did a measurement, it will point down. This is okay. This is the most subtle aspect of this entire paradox. If it's not clear, we should talk. Okay. On the other hand, if I did the measurement in the next run, for example, and I got that the spin is pointing down, then I am sure to get the other spin, the blue spin, to point up. Okay. Clear? And this is indeed kind of bizarre, because what this appears to say is that somehow my measurement 5 galaxies apart here on this green spin is somehow non-locally telling the blue spin which way to point. Okay. And this was the fact that led Einstein to say that this is bizarre. This cannot be true. Okay. Good. So Einstein said, this was not exactly Einstein. Why is it doing that? This is a Gedanken or a thought experiment. If I could do this, this would happen. But there are like physical processes with spins, it is very hard. But with photons, it is very easy to produce a situation where I get something like that Bell state because of some kind of momentum conservation or angular momentum conservation. That is possible with photons. That's where we'll get to, because the experiment was very hard to do with spins. That was why it was never done in the initial state years with spins or electrons. I mean.
These two are up and those two are down.
Mm-hmm. Yes, that's also a Bell state. That's the photon state that we'll create. Again, there is basically, in this case, they are anti-correlated. In that case, they will be co-correlated. No, no. This is something that we can also come to at the end. That's why I was very careful when I said that it appears as though the spin is communicating this information, but it is very, very clear from thinking about this in a little deeper manner that it's not like this spin sort of shouts out, ah, you point this way, I'm pointing this way. That's not happening. In principle, there is no transfer. This kind of correlation cannot be used to send information in the sense of, I cannot sort of use it to send superluminal information that travels faster than light. That's not what is happening. This is just a property that comes from a very interestingly correlated initial state. And that's where I'm going now. Okay. Yes, so let's go back to it again. That's very important. So the initial state I'm preparing, what is it saying? This is pointing up, this is pointing down. Plus minus, this is pointing down, this is pointing up. So if I measure, okay, so very fundamentally, these two states are what are called orthogonal. If you go back to my picture I had, this was a 1, 0, and the downspin is a 0, 1. So as a result, if I get this, then this is not important. And so if green spin is pointing down, the blue spin has to point up. Because I started with that state. It's the initial condition that is doing this. Okay. Yeah. Yes. It is broken. It is. That is because of the nature of the initial state itself. That's just what I explained. So after you've done measurement on one of them alone, you do break the entanglement, but I still know what is going to be the result of a measurement there. That doesn't require entanglement. I just require entanglement before the measurement. It's a very, very interesting question. This comes back to, again, what she was asking. It doesn't matter. The sequence of the measurements don't matter. So for instance, basically imagine these are billions of galaxies apart. They basically, what they will do is they will both measure locally, and then they will tabulate their results and then travel over billions of years and then come and look at how their results look with respect to each other. The point of entanglement is that these results are correlated. So this guy could have measured later, this guy could have measured before. No. I have to do many, many runs. As with everything in quantum mechanics, per pair, I can only do one set of measurements. The correlations are built up when I actually look at many results of many measurements. We'll come to. Okay. All right. So then this is bizarre. And one way to explain yourself out of bizarreness that this creates, that's what Einstein wanted to do. If you still want to hold on to this realistic or realism idea, is to realize that there is one very, let's say, not interesting way in which I can produce similar correlations. Let me tell you what that is. So let's say my source is now like some simple classical object, and it produces two balls. These are classical balls. One is green and the other is blue. I produce these two red and green balls, and then I basically take another big box, cover these red and blue balls, shake this thing around, and then cut the box exactly into half, right? Which will mean that I'll have two black boxes. I do not know which color it is inside this black box, and then I send them out far away. Then what happens? Now, as soon as I make a measurement in this far end and see that there is a green ball, I know for sure there is going to be a blue ball at the other side. Okay. Similarly, if the opposite happens, I open this black box on the left side, I see basically a green. I will definitely see when the other guy opens, I will see a green ball, right? So if I get blue here, that's green. If I get green here, that's blue. So this looks and sounds very similar to what was happening in a sense, like with these spins. But then this experiment, I'll throw it away. That run, I won't like it. So I'm just making sure that you could have taken 2 black boxes to begin with. You close your eyes and put it on top. It's as simple as that. Or if you want, it's like you can use a shoe. I'll come to another simple example. You can use a shoe, that left and right shoe. I don't know which one goes. If I find left here, the right will be there, like that. Okay. Now, even though this looks and feels very similar to the spin experiment, remember what this is telling you. This is telling you, I do not know what is inside the black box, but throughout this travel, the black box had a definite colored ball in it. It can change from run to run, but it definitely had some fixed color. That is what realism is. Okay. So Einstein said, yes, this has to be what was happening with even these quantum mechanical spins. Okay. And this is what I was saying. So this is a cartoon and one of the best paper titles ever, which was called Bertelsmann's Socks and the Nature of Reality. This was a version of this Boxwala experiment that I described, where Bell wrote this paper, where he said he had a colleague, Reinhold Bertelsmann, who basically always wore different colored socks. So if you saw one of his socks was pink in color, you for sure know that the other socks that is hidden behind this wall will not be pink, right? So this is a very, very nice example of how Bell was really playful when it came to science. Okay, good. So now so then Einstein said, okay, now it has to be that really what is happening in quantum mechanics is that your description of the state, as I wrote it down, with up, down, down, up, and this superposition, that is incomplete. And what must be happening is that you have to supplement, like in the black box example, where I always knew what is going to be the result of the measurement even before I made the measurement, because there is always a definite color. My quantum mechanical systems and quantum mechanical states will have to be supplemented by extra information outside the purview of quantum mechanics as it stands. These are called hidden variables. And these hidden variables, what will they do? They will actually, without these two systems being correlated, they will locally tell, whenever I make a measurement, for individual measurements, they will tell me which way to point. It's really not this spooky action at a distance that is happening, but it is just that you did not look hard enough. Okay, so that is the idea of Einstein, but that is going to lead to extremely bizarre consequences. The most bizarre of that is the Bell inequality. But before I get to it, let me show you already a very bizarre consequence that was pointed out even by Einstein. So this is actually, I'm calling this as Einstein's EPR paradox. It turns out that Einstein presented it in a much more harder form. This is due to David Bohm, who is again one of the giants of quantum mechanics. Okay, so now if we believed in this realism picture, let's tell you what happens. I can show you a very weird consequence of this realism. So what does it tell me? I measured on this left end and I got the result that the spin is pointing down. Now I'm going to insist that even without measuring my right part, even without doing any measurement, I will say that it has to point up. So the spin is pointing up. I insist on that. That's what Einstein insisted on. And now I do something fun. Now I make a measurement of the spin along the x direction. Okay, then I'll get a definite answer that the spin is pointing in some sense along the x direction as well as the z direction. Or I get information regarding how the spin is pointing along the x as well as the z direction. Now, this is a very, very bad thing within quantum mechanics, because in quantum mechanics, observables like the spin along the x and the spin along the z direction, these are what are called complementary variables. So you might have heard a more popular version of this when you thought about the Heisenberg uncertainty principle, which tells you I cannot know precisely the value of x and precisely the value of p for any quantum system. Similarly, there is a law that prevents me within quantum mechanics precisely knowing the spin along the x direction and the z direction. But if I insisted on this local realism picture of Einstein, or this realism picture of Einstein, then I have to accept that I can tell x and z simultaneously. And that's one bizarre consequence. So something is weird about this insistence on realism. And basically, let's move on and understand that. How am I doing for time? Okay, so I am at a very bad situation with time. How do we do this? Is it interesting enough that I can go on for another half an hour, or if it is boring, we leave? Yes? Okay, good. All right. But feel free to leave when you get bored. I don't want to keep everyone. The door is closed, but it can be opened. Okay. All right. So now let's actually look at what Bell did. I promise that the number of slides decreases as we go higher. Okay. All right. So all of this comes down to this fundamental issue in quantum mechanics. As I said, before you measure, observables don't have any realism. So before you measure, unmeasured observables do not have any values within quantum mechanics. There is no sense in which they are real. So basically, what happened is when one way why the whole Einstein's EPR paradox did not sort of create a big rupture in physics, or didn't, because it's sort of telling you something very bizarre about quantum mechanics, but for a very long time, no one cared about it in physics because of a very important reason. The important reason, as I mentioned in the introduction, was basically due to the fact that Einstein is just telling you that your description of quantum mechanics is incomplete, but it is not wrong. So there is a plethora of experiments that were happening simultaneously, which could all be explained perfectly and beautifully by using quantum mechanics. And basically, Niels Bohr said, well, since this is happening, there is no reason why a quantum mechanical theory should have this realism like classical mechanics. It's just inherently different from quantum mechanics. So basically, just shut up and calculate, compare to experiments, keep doing science. And that was what was happening for a long time. Okay, before we go on to how this impasse in the way people thought about quantum mechanics was broken, let's ask, how would you actually break this? So if we took Einstein seriously and said that there have to be some hidden variables that you have to give in addition to the quantum mechanical state, the sort of things I wrote down like up, down, up, how would it look? Okay. Now, basically, the idea for a hidden variable theory, very pictorially, is like this. I won't go into a lot of mathematical details, but basically what is happening is when I send my pairs of particles, in addition to my state, I have to also specify some parameter lambda, okay? And that lambda will actually dictate basically what are going to be the results of my measurement. This lambda parameter, or this hidden value parameter, is local in the sense that whatever is happening here is completely independent of what is happening here. Okay, all the experimental measurement results I get for such an experiment should be described by these hidden variables. Okay, so let's actually explore a little bit how, because we are going to move more and more closer to an experiment, let's explore how this whole business would look if I wanted to do an experiment. So quantum mechanically, the thing that I mentioned, that if I measure up, I'll get down. If I measure down, I get up. How would that be done in a lab? What I'll do is, now I've silently slipped in two very important labels to call the people that are doing the measurements at the left end on the green particle and the right end on the blue particle. This is Alice and this is Bob. And basically, let's consider a situation where Alice basically measures locally the spin along Z. Then Bob, for the same entangled pair, for the other half of the entangled pair, Bob measures it, and then he gets an answer up or down. Up means he will write down a +1. Down means they will write down a -1. Okay. Now the key point, if I started with up, down, and down, up, is after they have tabulated this and they compare their results, they will see a chart or something like this. Whenever Alice gets +1, Bob gets -1. Whenever Alice gets -1, Bob gets +1. Okay. Now, let's imagine, because we are talking about the fact that this lambda parameter or this hidden value parameter will tell you what results you will get independent of which measurement you do. It will tell you if you measure along the spin along Z, it will tell you what happens to the spin if you measure along X. All the information should be encoded into this hidden variable. Then Alice and Bob can choose to do a slightly different experiment. So what they can do is Alice will measure along Z and Bob will measure along X. Okay. Now again, the individual results of Alice and Bob, they will still be plus and minus 1 because it can either point forward along X, backward along X, and it can point upward along Z, downward along Z for Alice. Okay. They will again get plus 1, minus 1, plus 1, minus 1. And what is going to happen then is when you look at the correlations, this will become completely uncorrelated. Right? There is a minus 1, 1, 1, 1, minus 1. You cannot predict what it is. If you sum over all of them, you'll get a 0, actually. The reason, in some sense, is already apparent to us from the first set of pictures I showed you when I introduced quantum mechanics. What is happening is, as soon as Alice makes a measurement along plus Z, the state of Bob within the regular quantum mechanics is actually pointing, if Alice observes up, it's pointing down along X. Sorry, along Z. Now, this means that it's an equal probability to get forward or backward in the X direction. So that is completely random. Half the time I will get, half the time Bob will register minus 1, half the time Bob will register plus 1. So that basically kills all these correlations. So this is what quantum mechanics predicts. And the whole question where Bell starts thinking about these things is, can I construct a hidden variable theory? Doesn't matter what this theory is actually, such that I can actually reproduce such correlations without quantum rules. I have produced these correlations purely by applying quantum rules. Can I reproduce these correlations with such hidden variables? That is the question. Now, here is a slight sociological or historical aside. One more reason, apart from the fact of hidden variables or basically EPR not catching on because all experimental results could be described by usual quantum mechanics, was that at some point, immediately after the results of Einstein, Podolsky, and Rosen in 1930s, there was a very, very important and influential mathematician, mathematical physicist, John von Neumann, which some of you may know. He wrote a very important text about fundamental mathematics or mathematical foundations of quantum mechanics. And in it, he had a proof that basically answered this question I asked in the previous slide. Can hidden variables explain quantum mechanics? He answered it no, purely using mathematical reasoning. Okay, I put proof in quotes because this was done in 1932, and it turned out that this proof was actually wrong. Okay, and this proof came from a very influential mathematical physicist, and that again reinforced people not to go towards this direction. What is very interesting is, in 1935, just 3 years after von Neumann's proof, Grete Hermann, who was a philosopher / physicist who originally studied with Emmy Noether, some of you might know Noether, and also she was in Heisenberg's seminar group. She was like a postdoc with Heisenberg, and she actually pointed out a very important logical fallacy in von Neumann's argument. This was back already in 1935. What is somewhat sad is that even in the Nobel Prize citation, there is no reference to her. It shows how things are done. But at least this is, so the Nobel Prize sort of jumps from von Neumann. Rightly, Bell didn't know about her work, and Bell actually he actually showed the same thing. He showed that von Neumann was wrong. And then hidden variables continue to live on. And it was not interesting for the reasons I mentioned. Many people did not work on it until 1964, when Bell came up with a very interesting consequence of believing in hidden variables. Okay. Now, let me first explain what he's trying to do. He's trying to propose an experiment to rule out hidden variables. What is that experiment? It is precisely the sort of experiment that we were talking about. There is an entangled pair. I send one to the left, one to the right. And then now Alice and Bob can measure the spin, not along 1 or 2 directions, but they can actually measure along 3 different directions. They will independently choose which direction they measure. Okay. And they will evaluate the correlations between their measurements. Okay. So this E of AB is the correlation between the measurements when Alice chooses to measure and ask the question, is the spin pointing up along A or down along A, with Bob asking the question, is the spin pointing up along B or down along B? The correlations between those measurements are given by E of AB. I'll demystify this E of AB in a moment. But what Bell showed was, if you assumed that these correlations were produced by these hidden variable theories, they have to satisfy this inequality. So if I do E of AB with A and B along one direction and E of AB dash, then this magnitude has to be minus this E of B dash B has to be less than 1. So A, B, B dash are three different directions that are not parallel. That's all. Okay. And this is the famed Bell inequality. And let me just demystify what this E of AB is. All that happens is Alice is measuring along A. She gives pluses and minus ones. Bob measures along B. He gives minus ones and plus ones. Remember, now A and B are not exactly the same directions. So there is no way to say whether there'll be perfect correlation or perfect anti-correlation. I don't have that information anymore. So whatever it is, I can multiply the numbers. Okay. And that will give me this correlation for each run of my experiment. And this E of AB is just the average over these correlations. Okay. It's as simple as that. Great. Now, what is the crazy thing that happens? Now, if I use the rules of quantum mechanics, then I can actually evaluate what this E of AB should be, not according to these hidden variable theories, but as per the rules of quantum mechanics as it stands. And I can evaluate this E of AB, and it turns out it's really beautifully simple. It's just the dot product of the two directions they choose. Later, if questions are there, I can come to why this is the case, but this can be shown. And very nicely, what Bell did is he pointed out that if I choose A along Z, B dash pi by 3 is 60 degrees away from it, and B like another 120 degrees away from it. If I choose these three directions, this number S, according to the rules of quantum mechanics, will come out to be 3 by 2, violating this inequality from hidden variables, which tells me it has to be less than 1. Okay. So what he has done now, he's actually promoted this whole philosophical debate about, is there a hidden variable or not, into a testable prediction. If one could go into a lab, produce this, and do this experiment, you should either see this violation or not. If you see this violation, quantum mechanics wins. That's the description of nature. If you do not see this violation, maybe there are hidden variables. What we know now, to extreme certainty, there has been no experiment that has ever shown, there are several experiments that have shown violation of this Bell's inequalities, firmly establishing quantum mechanics is the way that we think it is. It is as bizarre as it sounds. Okay. And those experiments were done by these Nobel Prize winners. Okay. All right. So now let me move towards these experiments quickly. All right. So now, as I was explaining a little while ago, it's kind of hard to do these experiments with the spins of electrons. What one can do is one can actually derive an analogy. You all must have heard of polarization of electromagnetic waves. So these are basically the way the electric and magnetic fields point in a traveling electromagnetic wave. And if you take the quantum version of these electromagnetic waves, these are photons, and there is a strict analogy that you can develop between the qubits or spins of electrons and the polarization of photons. And it turns out that you can map the spin up along the Z direction to basically a linear polarization of light along X direction, and the spin down is polarization along an orthogonal direction. Similarly, the spin along the X direction that I was talking about is polarization along this 45-degree line that I'm drawing for the light, and the spin pointing backwards along minus X direction is analogous to basically polarization of light along the orthogonal direction to the plus 45-degree line in the XY plane. Okay. With this analogy, you can basically start doing experiments of the EPR kind with polarization with photons, basically. And that's what people did. So let me actually describe what almost all of the experimental setups for this experiments that were done by these Nobel Prize winners look. Very broadly, you will have a source, which would be some atomic system, which you apply some light or electromagnetic waves on. And then due to some conservation processes, it will produce 2 photons, always in the following kind of entangled state. It's a little bit different from the entangled state that we started with. It's not xy minus yx, but it is xx plus yy. But this is also entangled because remember, x polarization is mapped to upspin, y polarization is mapped to downspin. But this is still good enough. You get such a state that is produced. Then you send these 2 states away because these are photons. They also have momentum and they'll move away from the source. And what you do is you have at this point what is called a polarizing beam splitter. It's a very nice object. What it does is it basically, if I orient the polarizing beam splitter along the A direction, it will transmit whenever my polarization is along A direction, and it will reflect when it is perpendicular to the A direction. This clear? Similarly, if I put my polarizing beam splitter along B, it will transmit the B direction and it will reflect the B perpendicular direction, which means this is literally the kind of measurement I want to do, where I ask the question, is it up or down in spins? Okay. And then I can basically register these photons here. So the photon that comes transmitted is definitely in the state polarized along A. And if it is detected at D minus, it is definitely in the perpendicular state to A. So that's a +1 and this is a -1. Similarly, if I have this B, D plus, if I register, I have polarized light along B. This is polarized light perpendicular to B. And now I have what I need to do in order to calculate the correlation. I simply look at coincidence, right? So whenever I detect plus and plus, then this means both of them are along the along the same A and B directions. N plus minus means that one is pointing along A, Alice's photon is pointing along A, and Bob's photon is pointing along B perpendicular, so on and so forth. And I can basically create the correlation between these measurements, this E of AB that Bell was interested in, from just this coincidence detection. And I divide by the total number of events. So this is a bit wrong. This should be N plus plus. This should be all plus. Sorry. Okay. So now all that happens is whenever Alice registers +1 and Bob registers -1, I will increase this coincidence by 1, so on and so forth. If both register 1, N plus plus will increase by 1, so on and so forth. These are the 4 possibilities that I get for the coincidence results. And this will help me construct this E of AB. Now, what our first Nobel laureate Clauser did, was he converted the original Bell's inequalities into a very, very interesting version purely based on these polarization measurement. He asked questions about this particular combinations of polarization. So I can, for this, I would need Alice to be able to measure along 2 directions A and A dash, Bob to be able to measure along 2 different directions B and B dash. And you make up this combination where I look at correlations between AB, A dash B, A dash B dash, add them and subtract the correlation when I get between A and B dash. Now, it turns out that purely from this hidden variable theory, this leads to a following Bell inequality, whereas the quantum mechanical prediction, just like it was minus A dot B with the spins, it is simply the cosine of the angle between A and B. Okay, and immediately Clauser, who wrote this paper with Holt, Shimony, and Horn, he was able to point out that if you took the following kind of configuration where A, B, B, A dash, B dash are equally separated by the same angle, then the quantum mechanical correlation that you would get, quantum mechanical value you get for S, is going to be larger by is going to be 2 times square root 2 or minus 2 times square root 2, depending on which angle you choose, clearly violating this Bell inequality. Okay, so this means that if you go to a lab and you make this, you should be able to see whether is this happening or is this correlation always bounded between -2 and 2. Okay, good. So let's forget about this, not so important. Let's now get to the big experiments that were done by this. It is a variation of Bell's. It is exactly the same logic. It is just with photons. That's all. Okay, so now let's look at a very short digression of John Clauser, who I called brave a little while ago. He did his PhD actually in Columbia in molecular astrophysics. It turned out that he was always interested in quantum foundations and quantum mechanics. But even starting from his PhD, he was actively discouraged from working in it, precisely because of this shut up and calculate feature. Like, I mean, what is the big deal about this whole thing? Everyone understands quantum mechanics. It's predicting the right results. Why are you worried about this nonsense? But he did not let go. After he finished his PhD, he got a postdoc to work with Charles Townes, who's another Nobel Prize winner. He discovered the laser, if you want, one of the discoverers of lasers. And he actually joined him ostensibly to work on radio astronomy. He said, I'll work on radio astronomy. And he went there, but with a plan, because an earlier PhD student of Charles Townes had built an experiment that could be used to do these experiments that I mentioned, like these EPR experiments we just showed, like polarization correlation detection experiments. And he said, like, I'll work on this. Half of his time was only allotted to it. So Charles Townes was very clear. You have to spend half of your time on this, but and he got a PhD student also to work with. And he ended up doing this. But he was doing this with a great amount of personal risk at the time when it was very clear from multiple quarters that essentially working on things like quantum foundations meant that you don't have a career in physics. For instance, what was really amazing is this is one of these cases where someone actually created a field more or less entirely by themselves, because Bell wrote his papers in 1964. And Bell says in conversations that until 5 years after he published his paper, saying something that is super important to physics, no physicist ever contacted him or talked about this research to him in person. Clauser was actually the first physicist to actually even get in touch with him and ask him, has there been an experiment on this? Is it worth doing an experiment on this? I want to do this. And it turned out that is amazing. No less person than Richard Feynman kicked him out of his office, Clauser, when he went to try and explain to him. So as I said a little while ago, he made a version of Bell's inequalities that could be tested in the lab. When he tried to go to Caltech, because he was an undergrad from Caltech, so he had a very long historical connection to Caltech. His parents went to Caltech and so on. So he wanted to explain his latest results on Bell's inequalities before doing the experiment to Richard Feynman. And Feynman basically summarily kicked him out. He said, like, just get lost. What are you talking about? If you have an experiment that actually contradicts quantum mechanics, come to me. It's kind of a bold-faced statement. But he persisted and he made this beautiful experiment. Let me just briefly describe what he is doing. In the first iteration of the experiment, all that is happening, let me first explain what is one thing that he's been able to do. Unfortunately, he could not sort of he could make his polarizer point in multiple directions, but he could only count situations where the polarizer let the light through. So he didn't have a polarizing beam splitter. This polarizing beam splitter is a very new thing. I talked about it as if it has been around since the age of whatever, but it was something that was recent. At that time, that was not there. And so what he had was just one polarizer, one analyzer at this point, like the kind of analyzer you would have in the lab. And he could make it point in different directions. But this meant he could only detect whenever the photons that came to him were parallel to that analyzer's direction. So he could only detect one kind of coincidences, which are like both pointing along this. I make this along A and I make this along B. If both photons point up along A and up along B, then you could detect a coincidence. Okay, and that's all he did. But he was smart enough to rewrite the Bell's inequalities again to be able to also construct a violation for this situation, where basically this number that I'm writing down is the coincident rate when the angle between the two polarizers at these ends are 22.5, which is like pi by 8, I think, and 67 by half, which is 3 pi by 8. So when I just take coincidences along these two rates for these two configurations, when it is separated by this and separated by this, you again get a modified Bell's inequality. So a short comment on the source. The source was basically, he had a calcium atoms, which he sort of used a hydrogen arc lamp to excite. And when you excite this calcium atom to a higher energy state, it comes down to its ground state by actually emitting 2 photons. And these 2 photons are emitted in this entangled state I talked about, XX plus YY, and they also travel in the opposite directions. Okay, that was arranged for him. And what was nice was, first of all, here is a plot. These are plots that are beautiful because what you see here is pointing the coincidence rate as he varies the angle between the two polarizers as a function of the angle between them. Okay. And this curve that he's drawing here, this is not some fit. This is really what quantum mechanics predicts. You can see this experiment was not particularly sophisticated, but already indications are that quantum mechanics is excellent. No one thought otherwise. What is more important is when he looked at this quantity, which was this Bell's inequality, he found a violation, right? Up to many standard deviations. It had to be less than 0, but it is 0.05. Okay. And that was the first ever test of Bell's inequalities. Good. Now, what else? So then comes along our second Nobel Prize winner, Alain Aspect. Let me just describe what he did. He did actually what Clauser actually proposed in his original paper. Remember, you had to have A, B dash, A dash B, A dash B dash, and you had to count when the photons were either parallel to A and B or parallel and perpendicular to A and B dash and so on. This was the original inequality of Clauser. And in his better experiment, he managed to finally get in 81-82, get a polarizing beam splitter, which actually enabled him to do these experiments and test the original form of the Clauser inequality. What you see here is this correlation coefficient S, and you can see clearly the hidden variable theories point that it should be between -2 and 2, and he finds these beautiful regions where it is violated, right? For these, this is basically the angle between A dash, B, and B dash. That angle that you choose that maximally violates the Bell's inequalities. Okay. And these are from real experiments. And you can see these already. One of the other important things is the error bars are even lower than the Clauser experiment. That's what I meant when I said he improved these experiments a lot. Okay. Good. So now, sorry. Let me. So the intermediate region are angles between A dash, B dash, for which the quantum mechanical prediction is smaller and it falls within the hidden variable. In that region, you cannot say what is at work. But the key is that there are regions that violate, which tells you that, well, there is only one thing that can fit all of this. You can fit this part with hidden variables, but that is unsatisfactory. So you need quantum mechanics to understand the entire thing. Right. Okay. So then I can see some shifting. Last 5 minutes. Is that okay? I'm going to quickly talk about 2 experiments. This is what was the most important experiment of Alain Aspect. And then I'll just briefly talk about the set of things Zeilinger did. I won't go into any detail, but I'll just describe why they are interesting. And I'll finish. So one thing that is a little bit subtle about the way these hidden variable violations are recorded is that what can happen is if the 2 people that are measuring can actually talk to each other classically. So I can basically, if Alice and Bob can actually communicate on a time scale faster than basically at which my photons can reach them, then they can actually tell which setting to use. And actually, by this classical way of communicating, they can rig their results such that you will violate Bell's inequality. So the local hidden variable theory is not at fault. It is just that you allowed Alice and Bob to talk. They are not independently measuring. Okay. And if that happens, then your violation of Bell's inequality is in doubt. Okay. And this sort of issue where you make an experiment that tests violation of Bell's inequality, but you come up with a situation where you might be cheating yourself. These are called loopholes. And this particular loophole is called the locality loophole, which tells you whether are Alice and Bob separated enough so that over the time of flight of the photons, they cannot talk to each other. Okay. And to plug this loophole, Alain Aspect did his experiment. The principle of that is basically as soon as the photons are emitted from the source and they're flying over nanoseconds, they're going to reach your analyzer. Over that time scale, I should have a mechanism that flips the direction of my analyzers. Okay. If I can set up such a mechanism where I can switch polarizers extremely quickly over those timescales, then I'm in business. It turned out that that cannot be done. It's because basically the mechanical, because it is literally taking a polarizer and rotating it to give an electromagnetic signal and doing it, that would not work. So Alain Aspect came up with a beautiful plan. Come on. His plan was to basically create, he's now going to do the experiment that Clauser did originally. So he's not sort of looking at parallel and perpendicular. There is no polarizing beam splitter. Okay. All that he does is when the photons come towards the two sources, there is basically a switcher C1 and C2. I'll tell you what these switchers are physically, but this is like a switch that will allow the photon to go along this direction or this direction. If it goes along this direction, I will actually have a polarizer waiting there, an analyzer waiting there, which is pointing along the A direction. If it goes along the second one, I'll have an analyzer waiting in a completely different direction, A dash. And now this idea that I said where I have to switch the direction of my polarizer boils down to making a switch that allows me to go in this direction or this direction fast enough, right? Instead of dynamically varying the analyzer direction, he just made two channels and he said, can I vary how fast I can put the photons into these channels? And he actually did that using a very, very simple setup, which was just basically he created a phonon or a standing wave of, I think this was light, of water. And basically, if there is a standing wave of water in between at this point C1, then I will deflect the beam. If I turn off the standing wave of light, basically I'm sort of literally turning the photons mechanically. If I turn off the standing wave, then it will get transmitted. So then all that I have to do is very quickly switch on and off a standing wave in my medium. Okay, so this is just the basics of what nowadays is called acousto-optic modulation, if some of you come across this. And this is amazing. And with this setup, he was able to actually do the following. He switches this between on and off state over time scales of 10 nanoseconds, whereas the time of flight, which is the total length L divided by C, is 40 nanoseconds. So over the time scale over which it is flying, I'm already switching this. Okay. And remember this number for a moment. He did this experiment when it was about 12 meters. Okay. That was the largest distance, and that was enough to plug this locality loophole. And he could actually see again a violation of Bell's inequalities. So there was no issue. When you plug the locality loophole, it still worked. Then one of the things Zeilinger did, and then I'll go to more interesting things, in as far as Bell's inequalities go, is he plugged this locality loophole even better. Time varying analyzer. No, he's saying that the analyzer's orientation is varied as a function of time. Effectively, you're doing that here, right? Because I do not know which way my photon, which analyzer it's going to do. It's a discrete variation. I'm varying between A and A dash discretely. Time varying, we have now ways to vary it like continuously also. Yeah. Okay. All right. So then Zeilinger did a better version of this where he actually started. This was an experiment that was done in Innsbruck in Austria, where he actually managed to make a separation between Alice and Bob that was of the order of 400 meters. So 12 to 400 meters. And over those distances, you could distribute these entangled photons and verify Bell's inequalities. But already some very interesting upgrades happened. One is the fact that these sources of entangled photons became more modern. These are called nonlinear crystals, and you produce entangled photons via completely different process here. But what is a little bit more interesting is he also started plugging another loophole. This loophole is called the freedom of choice or settings loophole. What is it saying? It's basically saying in the Alain Aspect experiment, when I do the switching, this is done very deterministically. He basically puts a signal generator and basically turns on and off that standing wave that will push towards one arm or the other. But that is also somewhat of a problem, because in principle, this means that my analyzers have memory. So my analyzer, the direction in which it is pointing, I can write it as a function of time, and it is changing not randomly, but I'm doing this some way deterministically. Turns out that that can be a loophole for Bell's inequalities. And it turned out that Anton Zeilinger was one of the first people who started using very nice random number generators in order to switch these analyzers fast enough so that there is no memory effects. So that's the freedom of choice loophole. Okay. The best random numbers are from quantum mechanics. So that's a good point. So let me just tell you what he did for the greatest ever test of this. So what he did is, like, he started generating random numbers based on cosmological sources, or just stars that are so far away that there is no way they could have correlated over billions of years ago. So that sort of, in a way, it's like seeding very far back. He's putting the seeding to billions of light years away. Even with that, it didn't break. So this has been done also. So he generated random numbers from that. But what is very interesting is quantum mechanics is the best known way to generate random numbers. These results of measurements, I said, right, which are completely not deterministic, you can easily create a random number generator with that. And there is a lot of research on quantum random number generation. Okay, great. So just the last 2 minutes, what Zeilinger did, apart from plugging these loopholes, is that he realized that entanglement is useful. In a very quick manner, let me just say 3 things he did. One is he did something called teleportation. What that is basically, that's a way to transfer the quantum mechanical state of one photon to another photon by using a Bell state. Okay, and this is very important if you want to use quantum mechanics for communication and so on. Okay, that's one thing he did. We'll get into details if you're interested. The second thing he did is something that is very beautiful and something that I understood well only yesterday, but still, I'll just mention this. This is called quantum key distribution. What this is whenever you have cryptography where I want to send messages that are hidden from a party A to party B, what I have to do is basically, nowadays, I do not have to hide the way I encrypt and the way I decrypt. I can put all of the sensitivity into something called a key. Okay. Now, if I have this key, which you can imagine is like this, what you call as this PIN code that you get when you make bank transactions. If you're able to securely give these two parties securely a key that no other eavesdropper can find out, then you make your basically your cryptography process very secure. Now it turns out that, for the lack of time, I can't talk more about it. It turns out that the best way to do it is by actually distributing 2 photons in, or many copies of these photons in these entangled states. Using these entangled states, you can make the most secure keys that you can distribute between 2 people. And that was proposed by Arthur Eckert, and it was experimentally verified by, let me go here, by Anton Zeilinger, where he securely distributed a quantum key between 2 islands in Europe, in Tenerife, in Spain, and La Palma, over 144 kilometers over this length scale. So I'm putting this length scale explicitly because we started in the ASPE experiments at 12 meters. So now it is 144 kilometers. That is one thing. Let's not talk about this entanglement swapping, which is also interesting. But let me come to the final slide. Where are we? This is not so important. Finally, what is the state of the art today, 2022? The state of the art for distributing is held by China now. So what they managed to do is actually distribute this secure quantum key from a ground station to a low orbit satellite, which was made specifically for this purpose, called Mischius, and then connect via this satellite to another ground station. And the total separation between them is 1,200 kilometers. So from 12 meters to 12,100 or 1,200 kilometers. So we've come a long way, and this is just the beginning. There are lots of interesting things that entanglement is teaching us. One of the things that is particularly interesting is entanglement is not just about these Bell's inequalities experiments anymore. You can use this for quantum communication and so on and so forth, but it is now leaving its imprint everywhere. One particularly nice area, which, for example, Arpan works on, is this idea of entanglement entropy in strongly correlated condensed matter systems, or even like high energy physics systems, where you have quantum states of many body systems, where the only way to understand their behavior is by analyzing how they are entangled amongst each other. So that's like changing the way we are thinking about condensed matter physics. Moreover, when it comes to gravity, there is also some very beautiful connections between entanglement and gravity that have come up. I won't talk about it for lack of time, but this sort of just to reinforce that entanglement is essentially everywhere. All right, the very last slide, and this is, I should have put this as the first slide. This is a mosaic of John Bell made with essentially all the scientists that have contributed to this extremely important field. This is just to show that this is a complete community effort. So these three small squares are the three Nobel Prize winners. Of course, the Nobel Prizes recognize only a few people, but it is to reinforce that science is produced by a very large community. This is just my sort of tribute to them. It was originally by, it was in PRL that they released this. And yeah, that's it. Thank you for your attention. Sorry for the very long